I'm now live streaming. Today is the wave specification annotation. I've got my chat on a different screen, so that's exciting, on the iPad. Yeah. There's nobody here, but that's okay. I think I'll just start talking anyway and see how we get on. So the top of the specifications, we've got progressive waves. Ooh, George is here, and Will. Isn't that good? Good to see you. So let's talk about waves. The first point in the specification says oscillation of the particles of the medium. Hey Sam. So that's what a wave is. So a progressive wave is a wave that moves. I hope you like my rubber duck. I did steal it from the internet, but that's okay, I think. So in equilibrium, the particles are at rest, they are not moved, and then as a wave, so if we had a wave pulse, then my little rubber duck would be displaced from equilibrium. Okay. My rubber duck is a representation of the particles in the medium. So in this case, moving up and down. Now, what we need to remember is my duck moves up and down, but nowhere else. The wave travels. The name for the way a wave moves is propagating. So we'll talk about wave propagation. So to the right is the direction of wave propagation if my my displacement is moving that way. And my rubber duck, which is a representation of the particles in the medium, is moving up and down. So it goes up to here, and then let's say down like that, always about the equilibrium position. So our particles oscillate about the equilibrium position. They move up and down, up and down, up and down. Or they might move forwards and back, and forwards and back, and forwards and back. We'll get to that in a minute. That's a bit of a mess over there, so I think we'll get rid. Amplitude, frequency, wavelength, speed, phase difference, C equals F lambda, F is 1 over T. So quite a lot in that one. If we draw, let's make it bigger. If we draw some axes, let's start with distance and displacement. So if I have my wave and I draw, so I can draw representations of waves like this most of the time. Actually going to make that slightly different. Okay, so this value here, this measurement, that's my amplitude. So that is the maximum displacement from equilibrium. To find the wavelength, so on these axes, to find the wavelength, I go from one point on one wave to the same point, don't want that one, to the same point on next adjacent wave. So we can go peak to peak, trough to trough. We can go from here, I don't know if that's on the axis, so from here to here. Very sinusoidal indeed. A lot of the time the waves that we draw will be sinusoidal, just to make it so it's easy to label. But you can have any shape wave and different shapes in this way give different they transfer different information. So in terms of a sound wave, if we plot the displacement of particles in a sound wave and they didn't look like this, then the information that they would convey would be the sound of the musical instrument. So phase, I'm trying to see which ones we can do on these axes. Phase is the part of a cycle a wave is in. One whole cycle, so one cycle is 360 degrees, or 2 pi radians. And then at any point during our wave cycle we could assign that a number of degrees. It's more interesting to talk about phase difference. So if I have this wave, and let's say, in fact, let's draw a green wave. Oh, stretched it. So if we I'm going to try and stay now. Whoop. With a constant phase difference. So here we have, so if, say the green wave goes past first, then the green wave gets to here before the blue wave gets to here. Okay? So we've got a phase difference between these two of a quarter of a cycle. So this one gets to this point a quarter of a cycle before the blue wave. So a quarter of a cycle later, the blue wave, or this part of the blue wave, will move up to there. So the phase difference between these two waves is 90 degrees, or pi over 2 radians. What have we missed? So I think before we do that, we need different axes. Get rid of all this stuff. I'm going to run out of space. So this time it looks very similar. Looks very similar, but on this axis we've got time, and this axis we've got displacement. So this is displacement of a particle over time. I didn't explain what medium was. So medium is the substance, the thing, the stuff that the wave is travelling through. So all waves, all mechanical waves need a medium. The type of waves that don't need a medium are electromagnetic waves. So this is looks very similar, but this time if I measure on the time axis between two identical points in adjacent waves, I get the period. So the period, capital T, because it's a special kind of time. The time is the time for one full cycle. Of the wave. The frequency is the number of waves passing a point per second, or the number of full cycles per second. So if I have a period t and I say, well, I've got 1 second, if I divide that by t, how many periods do I get in 1 second? Then I get my frequency. Yep. So frequency is 1 over period. So now we can talk about wave speed. So we know generally that velocity is displacement over time. If we've got a wave, for wave speed we're going to use c, and there is a reason for that, I can't remember. It's a word in a different language. So in time t, so in one period, the wave travels one wavelength. So if we've got frequency is 1 over capital T, then 1 over T multiplied by wavelength is the same as saying frequency times wavelengths. So that's our wave speed equation. And you'll need to know how to figure that out. Ace. Do we miss anything? Amplitude, frequency, wavelength, speed, phase difference, and those two equations. Excellent. Celeritas. What language is that from, George? C is for Celeritas. Latin. There you go. Excellent. So we're going to move on to longitudinal and transverse waves. We'll start with transverse waves. So in a transverse wave, if my wave is travelling that way, that's my direction of wave propagation or wave travel. Then my wave looks like this, and if I were to choose a point on that wave, the particle would be displaced perpendicular to the direction of wave travel. So in transverse waves, the direction of oscillation is perpendicular to the direction of wave travel. So you can say wave propagation. You can so let's start that one. Propagate space, or so there'll be a slash out there. Energy transfer. So essentially waves transfer energy and information. So the direction of wave travel is the direction of energy transfer. So in transverse waves, our particles go up and down and our wave travels to the side, one way or the other. So the direction of oscillation is perpendicular to the direction of wave travel. They are at 90 degrees to one another. We've got more people. Say hello, people. So longitudinal waves are a bit more tricky to draw. So I've drawn them as lines, so you can imagine this as a slinky or as regions of equal pressure in air. Hello, Vincent. Most of this will be relevant to you, Vincent. I don't think there's many differences between the IB and the A-level specs. Malice's law, though, you do need to know. We'll get to that shortly. Well, we won't do it, but I can do it separately. So, in a longitudinal wave, if we imagine a particle which is here, normally we talk about air. We'll talk about longitudinal waves. Sound waves are longitudinal waves. So in longitudinal waves, the direction of oscillation is perpendicular. No, that's a lie. It's parallel to the direction of wave propagation. Whoop. Okay, so longitudinal waves, the particles, and there will be particles because there aren't any longitudinal waves which aren't in a medium. The direction of oscillation of the particles of the medium is parallel to the direction of wave propagation. So if the wave is travelling to the right, the direction of oscillation is backwards and forwards. We've got different parts of a longitudinal wave. So this is a compression. That's where things are squeezed together. And then here we have what's called a rarefaction. So where things are spread out, where things are stretched, we call it a rarefaction. When they're squashed up together, we call it a compression. We can also measure wavelength. So in order to measure wavelength, I'm going to use a different colour to make it clearer. If we go from, it's easiest to go from the centre of one compression to the centre of the next compression. That would give you your wavelength. It's just easiest to do it that way because depending on the diagram, it's quite difficult to see where the centre of rarefaction is. You can do it from any position to any adjacent position, but I find it just easiest to go from the centre of one compression to the centre of another compression. Examples to include sound, electromagnetic waves, and waves on a string. Let's bundle those up then, shall we? Which ones of those are transverse? And which ones of those are longitudinal? So EM waves, electromagnetic waves, light, infrared, excellent. So electromagnetic waves are transverse waves. They include light waves or visible light waves, gamma rays, X-rays, microwaves, infrared, ultraviolet, microwaves. All of those are electromagnetic waves, and they are all transverse. Sound waves are longitudinal. We've got two types of waves in earthquakes. So seismic waves. We've got we've got pressure waves, we've got shear waves, which are also called primary waves and secondary waves. We normally talk about in terms of P and S waves. So S waves are transverse and P waves are longitudinal. Also in transverse waves we've got things like water waves. In fact, that's a really bad example because sound travels through water, so we can have compressions and rarefactions in water, so we can have longitudinal waves in water, so we don't use water as an example. But you could put waves on a string. Maybe with an example. Is Will dropping in and out? I can't see who's dropping in and out. Maybe I can. Participants. I only told you the participants in chat, not who's watching. Obviously we can have transverse waves on a string, so the ones that if you had a string and you shook it up and down, it would look like that. You can also get longitudinal waves on a string, so if you pull a string tight with two cups on the ends, then that's longitudinal waves travelling down the string. But we'll ignore that for now. Generally, you're going to want to use one of these four examples for examples of transverse and longitudinal waves. It does sound like a real problem, Will. Luckily, you'll be able to rewind and see anything that you missed. Students will be expecting the direction of displacement particles fields relative to the direction of energy propagation, and that all electromagnetic waves travel at the same speed in a vacuum. So for EM waves in a vacuum, wave speed equals 3.00 times 10 to the 8. That's really fast. 300 million meters per second. Really fast in a vacuum. Electromagnetic waves do change speed in different media, and we'll get on to that phenomenon refraction a bit later on. Polarization is evidence for the nature of transverse waves. So, polarization, you can imagine that you've got something akin to a picket fence or jail bars or something. This is 3D now. So if I've got waves which are going up and down and up and down, they can go through my jail bars and they're smiley. If I've got waves which are going side to side, which is really quite difficult to draw, they can't get through, so they're sad. So a polarizer, if we imagine, how else can we imagine it? So if we're looking straight ahead at a source of transverse waves, for example a light bulb, then although we've got displacement which is perpendicular to the direction of wave travel, the orientation, the plane of that wave can be in any direction. So these particles are coming towards us, or these waves, these field disturbances are coming towards us, and they're going up and down, up and down, down, up and down. These are going side to side, these are going like this, and these are going like this, but they're all coming towards us, so out of the page, or out the screen. Hi, Bayan. You get some studying in for physics. What we can do is we can put these through a polarizing filter. So let's go with a different colour, and we'll put it like this. Oh, I'm pressing the wrong button. So then only this one here gets through. That's almost true. So what happens is, electromagnetic waves, disturbances of fields are vector. They have vector components. So we get, everyone misses doing physics. If you're not doing physics, that's the postman. Another dog's barking at the postman. thinks he's done. Yeah, so all of these which have a component in the same orientation as the polarizer, that component will get through. So actually we can rotate polarization as well. So if this one was coming through, we'd get a component like this, adding to this component as it comes through. This one here, no, that one doesn't get through at all. That's got no component in the direction of the polarizer. So what we get coming out of a polarizer are plane polarized waves. So waves that only have one plane of oscillation, so they're either going up and down or left and right, or however they're oscillating, but that's the only direction that's coming out. And that's quite useful. I'm going to just draw that on screen. So longitudinal waves cannot be polarized. Transverse waves can. Yay. Application of polarizers to include polarimeter in the alignment of aerials for transmission and reception. So, I've got the right pen. So, applications of polarizers. So, why do we want polarizers? Let's imagine we're fishing and there's a very still lake, and sunlight is incident on the lake. Now sunlight has planes of polarization in all directions, but when you reflect light off a plane surface, it comes off polarized in the same direction as the surface. So if I've got my sunglasses here and my sunglasses are vertically polarizing, then we can cut out all of the reflected light from the surface. Okay, so polarizing sunglasses eliminate glare. And that's the same for polarizing filters on cameras. They also eliminate glare and they make your photo look different. Other uses have we got? We'll stick with that one. So it works for cars as well. Some 3D TVs use polarizing glasses. However, they tend to be sort of circularly polarized waves, so a bit tricky to explain. Aerials for transmission and reception. So you can get polarized electromagnetic waves like radio waves. It's a bit complicated as well. So if I have a transmitting aerial, and in my transmitting aerial my electrons are moving up and down, then I get plane polarized waves come out. So if I have my receiving aerial on a different axis, then it only gets a small part, so it only gets part of a component of this wave. So we don't want that. So what we want is to align our aerials in the same direction as the polarization of the waves. Lovely. Moving on. Principle of superposition of waves and formation of stationary waves. So, stationary waves are waves that don't transfer energy. They don't move, they don't transfer energy, they're just there being waves. So you can imagine having a skipping rope, wiggling the skipping rope up and down, and then the skipping rope being held at this end. So we've got a fixed point there, and as it comes back, it reflects. So we've got that wave going that way, and we've got our dotty wave going that way. And when two waves meet, they interact, they add together. Okay, so if I've got a wave like that going that way, and I've got a wave like that going that way, then they add together to make a really big wave. That should be equals. That should be add. So we add those two together and we get a really big wave. As this wave moves past, eventually it moves past, so they're like that, and this crest meets this trough, so this maximum displacement meets this maximum negative displacement, and then when they add up we get nothing. So as these move past one another, at some points we get maximum displacements, so the big adds, and some points we get minimum displacement, so we get nothing. And that happens over and over and over and over again. So some points actually never move, so these points here never move, and these points here are moving between a maximum and a minimum. You can do this with any two similar waves. They need to have the same frequency, and similar amplitudes, in order to get good superposition. This adding together of displacements in waves is called superposition. So when two waves meet and interact, we call it superposition. So if I've got one wave travelling one way and one wave travelling the other way, they're the same frequency, similar amplitudes, we can get a standing wave or a stationary wave. So these points here, the points that we said don't move, those points are nodes. And the points of maximum amplitude are antinodes. So here and here and here and here and here and here are all antinodes. So those are points of maximum displacement. What else can we say? There's a bunch of interesting things about these sections or these loops. If I call this a loop, then all of the particles on that loop are in phase with each other. So they all move up and down at the same time, and they have different amplitudes. So they all move up and down at the same time. They're all in phase, but all have different amplitudes. Adjacent to that, all of the parts of the string, in this case, in this part of the wave, are all in antiphase with these parts of the string. So when we talked about phase earlier, if we have a phase difference, I forgot to do this, of 0 or 360 or 0 or 2 pi or 4 pi or 720 degrees, we call that in phase. So if we've got a phase difference of a whole cycle, then we call that in phase. If we've got a phase difference of 180 degrees or 540 degrees or pi radians or 3 pi radians, we call that antiphase. So we can have different phase differences where it's not 180 degrees or 540 degrees, and the waves will be out of phase, but these specific values, so pi radians out of phase, is called antiphase, and if they're in phase, then they're a whole cycle apart. So if we've got two waves in antiphase, then they are of a phase difference of 180 degrees between them. So in these loops, all of the parts of the string in here are in phase with one another. They have a phase difference of 0, and all of the parts of this string, of this loop, are in antiphase with all the parts of this loop. So in adjacent loops, or between so from adjacent, we could say in adjacent antinodes are out of phase by 180 degrees, or adjacent antinodes are in antiphase, but all of the points on here are in phase with one another, and all of the points on here are in antiphase with all of the points on here. What else is interesting about stationary waves? So all of these have the same phase but different amplitudes, which is different to a progressive wave. So if this was a progressive wave travelling to the right, then eventually all of the particles on this loop would reach the same height. Yep. So if I imagine this one moving to the right, then this point here, as the wave travels to the right, is going to move up eventually. So all of the particles, or all of the disturbances in a travelling wave or a progressive wave, have the same amplitude, but no adjacent parts are in phase with one another. So I would have to go to the whole next cycle to find two parts that were in phase. So I could say maybe that this point here is in antiphase with this point here, but this point here and this point here are not on a travelling wave, unlike on a standing wave or a stationary wave, where all of these parts here are in phase and all of those parts are in antiphase with all of these parts here. So if I've got a string fixed at this end and fixed at this end, I can only have nodes at the two fixed ends. The first possible way that this string can vibrate is like this. Yep. This is going to be our first harmonic. Just check. So on a string, we can have our first harmonic like that. If we have if we have more energy, our second allowed mode of vibration looks like that. These dotted lines are where the string will be half a cycle later. That's going to be our second harmonic. We can keep doing that. So for waves on a string, we get integer numbers of half wavelengths as our possible combinations on the string. So if I've got my first harmonic for a string, I've got one loop, second harmonic 2 loops, third harmonic 3 loops, etc, etc, etc. There are other situations where we can form standing waves. So in this case, if I move this end up and down, or no, that's not a good way to think about it. If I have two nodes here, so the string's fixed in both places, and I pluck in the middle, or I pluck somewhere along the string, then I get waves travelling in both directions which reflect at either end and come back and then superpose. So they add together to make a standing wave. Why aren't we using fundamental? Because it's confusing. If we stick to first, second, third, fourth, fifth harmonic, etc., then we don't have to use overtones. So if we use the term fundamental, then we can have a first overtone and a second overtone, etc., etc. Or we could just stick with first harmonic, second harmonic, third harmonic. This makes kind of more sense when we look at particles. We look at in the future we look at, or we won't look at, but in the future you could look at electron waves trapped in a potential well. That's for much later. But no, we're going to stick with harmonics and only harmonics. So these harmonics are going to have the same speed on the same wave, the same speed on the same string, sorry, but are going to have different frequencies, different wavelengths. I'm fairly certain, despite the fact that it doesn't say so, we need to think about some other situations. So if I've got a pipe which is open at one end, closed at the other end, or a pipe which is open at both ends, then at the boundary between the inside of the pipe and the air, we get reflection. But in that case, we get an antinode at the open end. Oh, look at that, that's tricky to draw. So this is the one that people forget to draw when we're talking about open closed pipes. So the length of the pipe in this case is the wavelength over 4. Yeah. So I've seen questions before that have asked about why would you want to use an organ pipe which is closed at one end and open at the other end rather than open at both ends. In this case, the length of the pipe is lambda over 2. So you can get much lower sounds, you can get much longer wavelengths with a pipe which is closed at one end and open at the other end than you can for an open pipe. So the rules are antinode at the open end, node at the closed end. And then it's your job to either remember or to figure out what possible ways you can make that happen. Oop. So those are our first 3 harmonics on an open closed pipe. For an open pipe, we've got antinode at both ends. Wow. Ooh, ooh, ooh. Oh, look at that. Not easy to draw. So for an open pipe, we've got antinodes at both ends. For an open closed pipe, we've got an antinode at the open end, a node at the closed end, and for a string, we've got nodes at both ends. These are our first, second, and third harmonics. First, second, and third harmonics. Okay. Interference. So, path difference and coherence. Coherence is one that they like to ask you the definition of. What? Morning, Tom. What? Where did the pipes happen? Where did the pipes happen? That doesn't make any sense. Shall I continue? That was the first thing you're hearing about pipes. Oh, that's good. You've learnt something. Yay! Do we not do pipes? It doesn't say in the specification that we do pipes, to be fair. I've always done pipes, because it's music. There are standing waves in pipes, or air columns, and those are the rules for standing waves in pipes. Oh, we missed this one. Ooh. We 100% did do pipes, George, but that's because you're in my class and I like pipes. It doesn't look like it is in the specification at all. Interesting. Oh well. A little bit of extra information. We missed a bit. Nobody told me. So, the bit we missed was this equation here. So, the frequency of the first harmonic on a string, so that's quite specific, 1 over 2 times the length multiplied by the square root of t over mu. Now this is a weird one because actually t, which is capital T, is not period, it's tension. And I think you'll find that you investigated this in a required practical. Mu in this case is mass per unit length, which we can measure, and then L is length. So what could we do? We could do things to change the frequency. We could measure the frequency, we can measure the length, we could keep the tension constant, and we could find the mass per unit length using a graph. In fact, we could do a graph of y equals, that's probably going to be x, or at least 1 over L or 1 over 2 over bx, and that one could be m, so then your gradient m would be root t over mu, and if you knew t, tension, because you've got a mass hanging off the end, so the setup would look like some kind of driver so there's mass hanging off the edge of a bench. That's a pulley. The tension in the string is mg, so we can know that. The mass per unit length we could measure. You can change the frequency, oh, what am I doing? This would only be one loop, because this only works for the first harmonic. So you can find the mass per unit length of the string, or you could measure it. You could know the tension, and you change the frequency on the oscillator. What else could you do? You could change the tension, measure the mass per unit length, and change the length in order to find the frequency of an unknown source. You can manipulate this in a number of ways to find different things and adjust different things, because actually all of them we can measure. But we did that for a required experiment. Okay, going to move on now. I think that's all of it. Interference. So path difference is quite straightforward. If I have a wave travelling that way, like this, and I have a wave travelling that way, like this, the distance that this one has travelled is shorter than the distance that this one has travelled from the same point. And we can find out let's do this. We can find out what that distance is if we know the separation of the two sources, and we draw a line perpendicular to the wave coming this way. This will be our path difference here. And then they arrive here, and the path difference tells us what's going to happen at this point. So if we've got a path difference of one wavelength, we get constructive interference. So the waves arrive in phase. They've gone through a number of cycles. Each one's gone through a number of cycles in order to arrive at this point, and they arrive exactly a certain number of cycles apart, or a path difference of lambda, or 2 lambda, or 3 lambda, or n lambda. So if we have a path difference of n lambda, we get constructive interference. So constructive interference, when we were looking at superposition earlier, the result of superposition of two waves when they add together to make maxima is constructive interference. If we arrive half a wavelength apart, we get destructive interference. So that's when the waves arrive in antiphase. That's like the drawing we did of superposition a minute ago, where we had a crest meeting a trough and they cancelled out. So constructive and destructive interference. This is our adding to make a maximum, and this is our adding to make 0. Coherence, or should we say coherent sources, have the same frequency that's kind of different, have a constant phase difference. So it could be 0, it could be something else, but two coherent sources have a constant phase difference. So if two sources have a constant phase difference, then we say that they are coherent. In order to get interference which produces a pattern, which we're going to get to in a second, we need them, in order for them to have a constant phase difference as well, they're going to have the same frequency. So in order to get a pattern where we get constructive and destructive interference, we need coherent sources. They've got a constant phase difference and they have the same frequency. So one way we can get coherent light, because we're going to talk about light first. We can talk about anything. We can talk about water waves, any kind of waves will interfere with each other, will superpose. But for us, we're going to talk about Young's double-slit experiment. So we're going to talk about lasers as an easy way of getting coherent light. So back when Thomas Young did it, he had a light bulb which produces all kinds of crazy light. It gives you a spectrum, and there's no constant phase difference. You get all different wavelengths, all different frequencies. So what he did was he passed them through a single slit to get waves with a constant phase difference, and then he passed the waves through a filter, so he got all waves of the same frequency or the same wavelength. These days we don't need to do that because we can use a laser, and lasers are monochromatic, and monochromatic means one wavelength, and those can be very specific. So for example, for my laser pen at college, it's a red laser. It's got a wavelength of 620 nanometers. And tolerance isn't very good, it's plus or minus 20 I think, but you can get very good lasers which produce very narrow bands or single wavelengths. So the double-slit experiment, if we take our coherent light and we pass it through two slits, then what we find is, so say we shine our red laser like this, what we find is we get maxima and minima. We get bright spots and we get dark spots if we have a screen. Let's draw a screen. Those bright spots and dark spots show a pattern which kind of follows this shape. So if we have one slit, we'd get that shape. With two slits, we have multiple maxima underneath. Wow, how bad is that drawing? We have multiple maxima underneath this single slit diffraction envelope. We'll get to diffraction in a minute, it's a bit of a funny order. I'd like to have done diffraction first. So we get these bright spots and dark spots, and they get less intense as you move away from the centre to a point where you kind of have a dark spot, and then you have more intense, less intense, more intense, and we have these spots spreading out. So the width of this section here is double the width of this section here, but the spacing of these bright fringes, or these bright spots on the screen, is equal. You don't need to describe how laser works. It's not stated that you need to derive this equation. So on our screen we can measure. Ooh, I'm drawing under my webcam. That's no good, is it? Let's move that up. Is there a reason why we use red lasers more commonly than other colours? So for a long time, red lasers is what we had. Helium neon lasers produce red light. otherwise I don't know. They're just more commonly available, I believe. Easier to make, perhaps, or just been made for longer. We can get blue lasers and green lasers now. Sure, you can get purple lasers. Yeah. So we're using a red laser, and we're shining at two slits. The slits are separated by a distance we're going to call S. There's a distance between the slits and the screen, which we're going to call D. And then, since these are evenly spaced, the dark fringes are evenly spaced, the bright fringes are evenly spaced. If we take from the center of a bright fringe to the center of a bright fringe, that gives us W, which is our fringe spacing. Now if we were measuring that in real life, this was another required practical, then you would measure a lot, and then you would divide by, or one less than the number you have, to get the number of the number of separations. That would reduce our percentage uncertainty. We'll keep our percentage uncertainty the same, but reduce our absolute uncertainty. So if you take a large measurement with a certain percentage uncertainty, then you divide it by a number, then the percentage uncertainty stays the same. But if I have a small percentage uncertainty, then I have a small percentage uncertainty in my smaller value, so that reduces the absolute uncertainty in the separation. Wow, Waldo Radin is giving out free PSN codes live on his channel right now. Everyone can join. He is really live. I don't know who he is. George, do you want free PSN codes? Bless him. So, in order to find wavelength or fringe spacing, it's weird that we write it in this order. The equation we've got is the fringe spacing equals the wavelength multiplied by the distance between the slits and the screen divided by the slit separation. So if we wanted to rearrange that to find the wavelength, which we probably would, all the PSN codes, then we'd have the fringe spacing multiplied by the slit separation divided by the distance to the screen. Bum, 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 bum. Don't look at lasers. Much like you shouldn't eat radioactive sources, you shouldn't look at lasers. So lasers produce very, very bright light. It's very intense. It's in a beam. It all adds up. It's very, very bright. So a low power laser is way more dangerous than quite a powerful white light, because we get coherent light. It all adds up, and we get very, very high amplitudes. We get very high intensity. Hi, Matt. Very good to see you. What a way to start the day. I know, physics to start the day. Oh, getting hungry now, but we are getting close to the end. What have we missed? Interference patterns using white light. So if I were to use white light and I was to create a coherent source using white light by passing it through, I pass it through two slits, what I would see is not quite the same as this. Each one of these little dots would be spread out into a spectrum. So if I have this equation here, Kino Gaza, wow, what a name. If I have this equation here, Oh, I really fancy a fish finger wrap now. That's not very kind, Kino Gaza. I'm starving. So I have this equation here. If I decrease the wavelength, so if wavelength goes down, then fringe separation goes down. So if I have a shorter wavelength, for example, blue light, then my fringe separation would be less. If I have a longer wavelength, for example with red light, my fringe separation would go up. The net effect of that is I get my dots, so my middle dot would be white. My next dot, or the next part of my dot, and it might not be that it's spread out on the next one. You get different resolving powers for different slit separations, but we get spectra with I'm going to spread it out even more, with blue on the inside and red on the outside. Although that's not right. So what I'm going to do, I'm going to grab that, I'm going to save it for later, because when we talk about diffraction gratings, then we'll see that. But actually here we get the same spacing for each one. So if we had blue, we'd still have blue in the middle, but my peaks would be closer together. I hope you can see that really clearly, because that's a bit of a nightmare. Appreciation of how knowledge and understanding of the nature of electromagnetic radiation has changed over time. Big fights about whether it's a wave, whether it's a particle. Newton said it was a particle. Thomas Young said, hang on a minute, maybe it's a wave. And he set out to do this experiment to prove that it was a wave, that light was a wave. So electromagnetic radiation includes visible light. Most experiments back in the day were done with visible light. And it's good for us as well because we can see it. However, now, so we've gone from particles to light, particles to waves, but now we know that actually it's both. So we have what's called wave-particle duality, and photons behave both like particles and like waves. That's for a different day. We could do the same thing as this if we had, whoops, I don't want to brush that big. Two please. If I have two speakers, so my two speakers are two coherent sources, and you can see that these add up. So if I'm going to the middle, then I get a path difference of 0. So it's going from there to there. It's like an isosceles triangle. These two are the same length. If I'm going over here, then the sound from this speaker has further to go, and the sound from this speaker has less far to go. But we will get a loud point if the path difference is what? And lambda. So here we'd have a path difference of lambda if that's a loud spot. We all done? Yeah. Okay. Diffraction. Oh, 2 sections left. Talking to myself. I do feel like I'm talking to myself when I'm doing this, which is good. So the appearance of a diffraction pattern from a single slit using monochromatic and white light. So diffraction grating, if you imagine taking our double slit and adding slits, loads and loads and loads and loads and loads of slits. Loads and loads and loads and loads of different slits. No, the same slits. So a bit like our jail bars that we had earlier when we were talking about polarization. That is a diffraction grating. So our light is instant on the diffraction grating and diffracts, so spreads out as it goes through each one of those little gaps. And each one of those little gaps, the waves coming from the other side, spreads out and interferes with all of the other ones. Puts the diffraction back with a single slit using monochromatic and white light. So we have, for our white light, we get a maxima in the middle, which is going to be white, because all the path difference form is the same, they're all arriving in phase here. But as we spread out, we get more spreading out of the red light than the blue light. The blue light doesn't spread out as much. Ooh, derivation of d sine theta equals n lambda. So for a single slit diffraction. Aha! Right, ignore everything I just said. This one down here is going to go with a plain transmission diffraction grating. This is for a single slit. So we did talk briefly about a single slit before, and what we said was that we had this kind of diffraction pattern. So the way that we'll describe this is using Curran's model of waves passing through a gap, or model of wave propagation. So every single point in that gap creates its own circular wavelets, and what we get is spreading out like this. But the waves from the top can interfere with the waves from the bottom, so we get bright spots in the middle, over here, and over here. So this is interference with, the way we think about it is interference with from the waves coming from top and the waves coming from the bottom. We get the most spreading out in the same way as we did with our equation earlier of the waves with the longer wavelengths, and less spreading out of the waves with a shorter wavelength. So if we had a white light source incident on this slit, we would see these spectra spreading out on the screen. I mentioned briefly that if that width between or the width of that maxima is W, then the width of the central maxima is twice that. Qualitative treatment varies from the width of maximum wavelength and slit width. So we don't need to do a graph of this, which is good. We don't actually use an equation for diffraction, which is a bit annoying really. So if we have this for my own use, the half angular width of the central maxima is lambda over b. So if we increase the wavelength, so we get longer, then this the width of this spreads out, it gets wider. If we decrease the wavelength, so if we get like blue light, then this gets sharper. Okay, so we've looked at one slit, we've looked at two slits. Now, what if we have all the slits? So that is, if we have all the slits, we call it a diffraction grating. We get loads and loads and loads of slits, and what we usually get is something like it tells us how many lines there are per millimeter. Now that isn't very useful to us. What we really want, if we call this, well, let's call n lines per meter. So in this case we've got 300 lines for every millimeter, and we've got 1000 millimeters in a meter. You've got 1000 lots of 300 lines, so n equals 300,000 lines per meter. So the units would be m to the minus 1. If we want to find the distance between the slits, so between there and there, then we're going to do 1 meter divided by n. So if there are 300,000 lines in every meter, what is the separation of those lines? So if we take 1 meter divided by 300,000, we'd find d, which would be our slit separation. Okay, use of spectrometer will not be tested. Let's have a quick think about diffraction grating, or applications of diffraction gratings before we do the derivation, because I'll clear all that up. So we can use diffraction gratings to split light out, a bit like a prism. So it does a similar thing to a single slit, and we can get spectra from different light sources through a diffraction grating. The application that they normally want are going for is the analysis of star spectra, or the analysis of the composition of a star's atmosphere. So when we split out these spectra, we get our complete spectra from a star, but we could also get black lines in it, which would be absorption lines, or we could, if we had a light source of a single atom, we could get emission spectra, and if we pass that light through a diffraction grating, then we can see those absorption spectra and we can measure them. Okay, let's think about our diffraction grating like this, and we're going to think about let's go with laser light instant on my diffraction grating. So from my diffraction grating I get a dot in the middle, I'll get a dot out here. So diffraction gratings give us very sharp peaks, so they give us very sharp peaks compared to single slit and double slit diffraction, which is good if we want to see very precise, or we want to take very precise measurements of wavelengths. So if we look at this point up here, we're going to see a dot here, a dot here, and a dot here. This is going to be what we're going to call our 0th order maximum. This will be our first order. This will also be our first order. And then maybe we'll have second order. We'd have one of these at the top as well. If we think about this one up here, we've got waves coming from this slit and from this slit. We know that they're coherent. If we zoom in on that spot there, then we've got two slits like this. We've got our light going away like this, eventually meeting up to be our first order maxima. What we can do is what we did earlier to figure out the path difference. We can use this triangle. So on this triangle, the slit separation D is the hypotenuse. This is a right angled triangle. This section here is lambda, that's our wavelength. This angle in here actually is the same as this angle here. So with a little spot of trigonometry, we know that sine of an angle is equal to the opposite side, which is lambda, over the hypotenuse, which is D. Now if we're looking at our first order maxima, then that's our angle there. If we're looking at our second order maxima, then our theta would be there, and we'd get a different path difference. So these correspond to where we've got a path difference of one wavelength or a path difference of two wavelengths. So we can put an n in front of lambda. This will come up again in our astrophysics bit. Yes, George, absolutely. We'll take a look. Oh, excuse me. We'll take a look at star spectra in terms of analysing the composition of stars' atmosphere. We rearrange this to get the equation we've got above, so we get d sine theta equals n lambda. Ace. Now, we only get a certain number of orders, or a certain number of maxima, and n will tell us how many we're allowed. If we say n max equals, then we can't have any orders which are past 90 degrees. Okay? We can't have any orders which are past 90 degrees. So if we make theta 90, then n max is going to be d divided by lambda. That's our maximum number of diffracted orders, where sine theta equals 90. You also have to remember to round down. Because if it's bigger than 90, so if n max is say 2.6, to see if we rounded up to that third order would be an angle bigger than 90 degrees. So we always have to round down. Cool. Refraction, and our last section. So refraction is the speeding up or slowing down of a wave when it passes from one medium to another. So if I draw a boundary, and let's start simply. That's a vacuum, and that is glass. So this medium here is glass, and this medium here is a vacuum. If I have a ray of light incident on, in fact, let's go straight down. Incident on this boundary. As it enters the glass, it will slow down. Okay? What refractive index means is it tells us how much it slows down by. So N is our refractive index. In the substance, light travels at a speed cs, and in the vacuum, light travels at a speed c. So to find out how much slower light goes when it enters, we do c over cs. So a light entering a medium from a vacuum, our refractive index is a measure of the slowing down of the wave as it goes into the medium. So we can do this with any waves. We talk about it quite a lot when we talk about light going from one medium to another, but it works just as well for other waves changing medium as well, sound waves for example. Students will recall the refractive index of air is approximately 1. So air has a refractive index, I think it's 1.00035, something like that. There are no units because it's a ratio of speeds. And that's very close to 1. Very close to 1 indeed. So we can treat air and a vacuum with both having a refractive index of 1. So if the speed of light in a vacuum is c, then the speed of light in air is very nearly almost c as well. So we can extend this. It doesn't have to be going from a vacuum to glass. We can extend it, so if we say we're going from medium 1 to medium 2, then if we take C1 over C2, we get N2 over N1. And also, the frequency stays the same. When our wave travel goes between across this boundary, our frequency stays the same. So the wave has the same energy. We get lambda 1 over lambda 2. If we change the angle of incidence, then as our wave slows down, or as our ray slows down, one side of the ray slows down first, and the other side of the ray kind of catches up to it. So our ray changes direction. We're always measuring, call that theta 1, call that theta 2. We're always measuring our angles from the normal to the ray. And you might think that this would be theta 1 over theta 2. However, if you plotted the graph, you would not get the relationship that you want. You wouldn't get a straight line. So what we do instead is take the sine of theta 1 and the sine of theta 2, and we'll divide those. So this is all of the relationships that we talk about when we talk about refraction. So light, if it's not incident perpendicular to a boundary, changes direction. If it goes from a medium with a lower refractive index to a higher refractive index, it bends towards the normal. If it goes from a medium with a higher refractive index to a lower refractive index, it bends away from the medium, away from the normal. So if this were to come out the other side, it would bend away from normal again. The light would speed back up, which is weird, but that's fine. We can rearrange this to find our expression of Snell's law. So if we ignore this one, ignore this one, then we get n2 over n1 equals sine theta 1 over sine theta 2. If we rearrange that, we get n1 sine theta 1 equals n2 sine theta 2. So you can tell angles of refraction if you know the refractive indices and the angle of incidence, or you can tell the refractive index if you know, excuse me, if you know some other things. You can use this to find refractive index or angle of incidence and angle of refraction. Now, what if my angle of refraction equaled 90 degrees? Okay, so if I'm in a situation where I'm going, let's go glass to air, and my light ray is coming out like this. What if, when it bends away from the normal, it refracts along the border? So my angle of refraction is 90 degrees, in which case sine theta 2 becomes 1, and we've found the critical angle. So sine of the critical angle equals n2 over n1. If we go past the critical angle, we get total internal reflection. So if we go past this critical angle like this, so we have an angle of incidence which is bigger than the critical angle, then we get reflection at that boundary. This only works, so we get total internal reflection when we're going from, we can get total internal reflection when we're going from a medium with a higher refractive index to a medium with a lower refractive index. Okay. Excuse me 1 second. With cold hand. Excuse me. So a use of total internal reflection is an optical fiber. Oh, I'm going to get confused between material and modal dispersion now. So an optical fiber is a glass fiber, or a plastic fiber you could have, glass is quite good because it's very optically clear, where you have a material in here called the core, and a material outside called the cladding. This is one type of optical fiber, and this is optical fiber with a step index profile, and that's the only one we need to learn about, which is good. So the core has a higher refractive index, so the refractive index of the core is higher than the refractive index of the cladding. So that makes sure that we have total internal reflection in the core. So if I were to look sideways along my optical fiber, and I were to shine a light in, not that we could see it, but the path the light would take would look like this. If we ignore refraction at these two boundaries, which we shouldn't. In an exam, you wouldn't. So coming into here, let's change this slightly. Coming in, we get a bending towards the normal, so maybe it came in like that, bent towards the normal. As it comes out, we get a bending away from the normal. So we have a refractive index of the core, which is bigger than the refractive index of the cladding. So we get total, so that's 4 total internal reflection. We get, what do you get? Another reason for having a cladding is if I put two cores next to each other, the refractive index would be the same. Yeah, so we have bundles of optical fibers in things like fibre optic broadband. We have bundles of optical fibers. If I put all the cores next to each other, the refractive index would be the same between the two cores, which would mean that the light could pass from one core to another core, and all your signals would get mixed up, and that would be bad. So our cladding makes sure we don't get any leakage of light from one core to another core. Material and modal dispersion. I don't like those names. So I'm going to have to check which way round they are. Actually, no, I'm not. So material dispersion means that. Oh, no, I will check. Oh, I will check. Oh, what's it doing? So in my head, I call these types of dispersion spectral dispersion and multipath dispersion, which makes sense. If we have red light, or if we have white light, so mixed colours of light coming in, then my blue light bends more than my red light as it enters the fibre, which means that let's go. So my red light bends less, and my blue light coming in at the same place bends more. And the effect of that is slightly then bend away from normal. The effect of that is my coming out the other side. Coming out the other side, I get some kind of spectrum, which is not what I want. So the way to get around this problem of having different path lengths for different wavelengths of light is to use monochromatic light. Oh, what's going on? Oh, I pressed grey. So that's to get around material dispersion. Modal dispersion would be if I was using all the same kind of light, but some of the light came in at this angle, and some of the light came in at a slightly different angle. Then I would get a path for this beam goes like this, and the path for this beam which goes like this. And again, we get spreading out of our data pulses, which is bad. We don't want that. So in order to get around modal dispersion, or what I call multipath dispersion, we use very thin fibers. So there's limited choice for the waves to take different paths. I think that's the end. I think that's the end. It's been a pleasure. It took us an hour and 45 minutes again. Thanks to anyone who was watching the whole time. Probably George and Will, maybe? I don't know who the second person is. I am going to go, and I'm going to cook some lunch because I'm hungry. And I might have a nap this afternoon. Nice. That took some good time, eh? We could do loads of these. We should do one for each topic, really. Maybe next time at a different time when there are more people around, when they're not having fun in the holidays. Gracious me. Anyway, as ever, it's been a pleasure. Breakfast time, Matt. Oh, crikey. It's 1:45. Yeah. Lunchtime, I think. Right. Thank you, Matt. Thanks, George. Good to see you. See you again soon.